everybody. Today we're doing vectors part 4. This is the last video on vectors. We're going to do 3 more example problems that will be similar to your homework and will most likely show up either on the take-home test or on the unit test. So let's get started. We've got 3 vectors A, B, and C all given to us. We've got vector A is 6i minus 8j. B is negative 8i plus 3j, and C is 26i plus 19j. Determine A and B such that little a big A plus little b big B plus C equals 0. So the strategy that we're going to use for that is we're first going to write our equations out, right? For this to be true, let's see, let me throw that up there. For this to be true, the i's all must equal 0 and the j's all must equal 0, right? So let's say we have 6ai from vector A minus 8b. Oh, you know what? These are all i's. Let's redo that. All right, so from vector A, we have 6a minus 8b plus 26 equals 0. And that's all for the i's. Then for the j's, right, we have negative 8a plus 3b plus 19 equals 0. So what I did is I took the I from A and put it there. Then I put the I from B and put it there. Then I took C I and put it there. Same over here. I took the J from A and put it there. The J from B, put it there. And the J from C, and I put it there. And then I put little a and little b where they need to go, right? Because you're multiplying that by the component of A and then the component of B, respectively. And that is for the J. Sorry about that. All right. So we have these 2 equations that must be true if AA plus BB plus C equals 0. All the i's have to cancel out and all the j's have to cancel out if that's all going to equal 0. So what we have here is really just it's a system of equations, right? So you've got 2 equations. What we'll do is we'll solve for A in one, plug it into the other, solve for B, get a numerical answer, plug that right back in, excuse me. So let's solve for A on this side. See, we have 6A equals 26 plus 8B. So A equals 26 plus 8B over 6. Okay, well now, that was easy. Let's plug that in. This will be less easy. We'll have negative 8 times 26 plus 8B all over, oh no, I did that wrong. I knew there was something wrong in there. Negative 26. All right. Let's do this. We have 8b minus 26 over 6. I like to put my positives first and negatives second. I'm weird that way. Plus 3b plus 19, that will equal 0. So on this side, we want to solve for b. So let's multiply that through. We'll get negative 64b minus 208, if you do that multiplication, all divided by 6 plus 3b plus 19 equals 0. Now we need to divide by 6. I'm going to narrow this. This is going to end up to 0.67. They're all going to be in 2/3. So I'll use the decimals. If you divide that, you get negative 10.67b minus 34.67 plus 3b plus 19 equals 0. Now combine like terms. You'll get negative 7.67b. Then you have, oh darn, what is that? 53, right? Oh, that's what I did. Negative up here times the negative here should give us a positive. I was wondering why that should be in the 50s, right? Yeah, 53. Okay. Plus 53.67 will equal 0. That was my bad. So we combined our like terms to get that. And here we combined these like terms to get that. Now solve for b. B is negative 53.67 divided by negative 7.67. That comes out to 7. So we've got B. This is really more of an algebra problem than anything, but figuring out how to set it up is the hard part. Once you get the two systems of equations, it's not too bad. So we'll take that 7, put it over here in the other equation. We've got our B over here. So A is negative 26 plus 8 times negative 7, all divided by 6. Put that all on your calculator. I believe that comes out to 5. Yep, it comes out to 5. So that's how you can find little a and little b in that kind of scenario. Use a system of two equations, go from there. The algebra can get kind of messy through here. As you can see, I screwed up on the negative there, so that can be tricky. And then it just takes a lot of time in a calculator, especially if you're doing this on a test. All right, next problem. This one, again, not too difficult. It's a derivative, so if we're comfortable with derivatives, this shouldn't be an issue. Now, the instantaneous position of an object is specified by its position vector r, leading from a fixed origin to the location of the point object. Suppose that for a certain object, the position vector is a function of time given by r equals 4i plus 3j minus 2tk, where r is in meters and t is in seconds. Evaluate dr over dt, and what does that represent for the object? So we've got this position vector, right? R equals 4i plus 3j minus 2tk. Now, if we want the derivative of r with respect to time, that means that we're only taking the derivative with respect to the t variable. Now, if you'll notice here, there's no variable. I is just a unit vector, it's just telling you direction. So that's not a variable. Here, there is no variable either. The only variable we have is this letter t. That's all we've got. So if we take the derivative, everything else is a constant. And if you remember, if you take the derivative of a constant, it becomes 0. So the derivative would be 0i plus 0j, derivative of 4 and 3 just goes to 0. Then the derivative of 2k is 2. So you'll subtract that 2. Okay, right there. But then we know the units, r is in meters and t is in seconds, so this would all be, whoops, step there, would all be in meters per second. So that's the derivative. What does this represent? Well, we started off with a position vector r, so this would be your velocity vector. That position vector, you can see that because we have this t, that means that you're starting 4 meters from start in the x direction, 3 meters from start in the y direction, and you start -2 meters in the z direction, but that is changing every second because there is a t there. So to figure out what it's changing, take the derivative. You've got the velocity vector. This velocity vector tells you that you are changing in the z direction only z direction by -2 meters per second. So it's constant velocity. So that is what that represents in a position vector. All right, now this one's a doozy. So this is going to take most of our time. In figure P3.66 that we have down there, a spider is resting after starting to spin its web. The gravitational force on the spider is 0.15 newtons down. The spider is supported by different tension forces in the two strands above it, so that the resultant vector force on the spider is 0. That just means that it's not moving. Right? All the vectors are balancing. The two strands are perpendicular to each other, so we have chosen the x and y directions to be along them. The tension Tx is 0.127 newtons. So we need to find in part A the tension of Ty. We are given Tx. Then for part B, we want the angle the x makes with the horizontal axis. And then we want, in part C, the angle the y-axis makes with the horizontal axis. So this is going to take some setting up. So let me do this. I am going to zoom in on this guy right here. Whoops. And we are going to set things up. So setting up this problem is the hardest part. Once it's set up, the math is not complicated. So first, we have a horizontal axis that they mentioned in the problem, right? That's what B and C are solving for. That means that we will also have a vertical axis. So this is our horizontal, this is our vertical. The angle for part B is the angle that tension X makes with the horizontal. So that would be right here, angle B. Now we can also use geometry to continue this circle and show that this would also be angle B. Okay. Now part C is asking about this, where does y, oh, my hand is making things move. Part C asks for this angle. Okay. We will also find that this is also angle B. And if we make this a triangle, which we will do right now because it will come in handy, that is our right angle. This is angle C. Okay. So these are the triangles that we're going to work with in order to solve this problem. Now there's one more thing that we're going to need to do for this. We're going to need to continue Tx, and this could be done by continuing Ty as well. We're going to continue Tx off in this direction so that we can get, let's see, right there. We need this right triangle. That right triangle is going to be important to getting our answer here. So again, if we follow through, this is angle B. We're not going to use that. We will have angle C here, and angle B will be down here. Okay, and if we would have continued Ty, we would also have, again, a B and a C, and that would make a complete circle of angle B's and C's alternating all the way around, as is in geometry, right? Now, let's go ahead and zoom out. That is what we're going to use for this problem. Now, let's set up the problem and write our givens. Okay, we'll do that over here. So we are given the fact that the tension, whoops, here, let me fix that. The tension, I don't remember what I had. Yeah, that looks right. Tension for the spider is downward, right? So it's 0.15 newtons. We'll just say it's down. Tension in the X strand is 0.127 newtons. We also just know in general, so we're breaking these into the horizontal and the vertical. So if we break these down into horizontal and vertical, we could say that the tension in X along the vertical, okay, which if we zoom in, tension in X along the vertical will be, whoops, that will be right here, tension in X along the vertical. Is that right? Is that the angle I want to use? I can't even remember. What is the angle that I want to use? Yep, yeah, that's right, that's right. Okay, so that's tension X in the vertical. Whoops. This right here is, I'll put it down here. This is tension X in the horizontal. Then here, this is tension Y in the horizontal. And this here, let me do that guy there so I can get room to write. This will be tension Y in the vertical. Okay, so we are looking at these triangles to solve our problem. Those are the two triangles we're going to use. So let's pop that back out. So the tension of X in the vertical, we have that guy written over there. We already know what the value is of the tension X. So that would be 0.127. That would be times sine of the angle B. Now we're going to use angle B for all of these. You could use angle C. It honestly doesn't matter, but part B comes before part C. So we're going to use that. Now, tension X in the horizontal, we want to define that. If you look up relative to angle B, that is adjacent. So you would use 127. That would be cosine of B relative to that angle B on the X triangle, the large red triangle. Now, let's do the same thing for tension in the Y. Here, we don't have the value tension Y for our vertical and horizontal, so that will remain in variable form. That would just be Ty. For this one, let's keep using B. So here, if we want to find, Ty vertical, that's actually adjacent to the blue angle B on that small red triangle. So that would be cosine of B, and then Ty in the horizontal, that would be opposite of angle B, so that would be Ty, sine of B. Okay, so notice that X and Y are opposite in that case. The vertical for X is sine, the vertical for Y is cosine. So that's just something to notice. Next, we will break up the tension of the spider, not in horizontal and vertical, but we'll split that up into X and Y so that it will play nice with our other tensions. So the tension of the spider in the X direction, if we look at this new triangle here, whoops, let me thin that line there. We use this triangle here, okay? That is what we're going to use for this. So if we want tension of spider in the X, which, let me finish labeling this, that would be tension spider X there, and this would be tension spider Y. Okay. So if we want tension of the spider in the X direction, that would be 0.15 in the X. Let's keep this relative to B, so that would be opposite, so that would be sine. sine B, and then tension of spider in the Y would be 0.15 cosine of B. Okay. So what we know is that this all needs to cancel out. So let's show that mathematically. If we have Tx in the horizontal plus Ty in the horizontal, that must equal 0, right? There is no pulling back and forth in the horizontal. But in the vertical, there is. So if we have Tx in the vertical plus Ty in the vertical, that needs to equal 0.15 because we've got a negative 0.15 due to that spider. So that's how the horizontal and vertical is all going to sort out. We don't have a horizontal and vertical for the spider right now. We split that into X and Y, and we'll see why we did that later. Okay, so let's continue on. Let's get to work. So that is how you set up the problem. We haven't even started solving anything. So the setup is the difficult part. Now that we have that, we'll be able to solve this relatively easily. Now, first, it's really hard to find the sides of a triangle without any angles. So we will solve part B first. Find the angle the x-axis makes with the horizontal. So first, we'll find part B. Once we have an angle, then we can find the other side of the triangle, which is the tension of Y. So let's use our givens. We have Tx and Ts. So if we say Tx plus Ts in the x, that must equal 0, right? And we have Ts in terms of B right there. So we can use that. So we have tension in the x, 0.127. The tension of the spider in the x is in the opposite direction, right? So that would be minus 0.15 sine B. That must equal 0. So let's solve for sine B. So we'll add that over. 0.127 equals 0.15 sine of B. Then we take that, divide it. Then you have sine of B. If you want to solve it, take the sine inverse. Divided by 0.15. Plug that into your calculator, you get 57.9 degrees. Like I said, the setup is the hard part. Doing the math is not very difficult. So what we did is we needed to find the angle B right here, right? Oops. Needed to find that angle B. They were everywhere due to geometry. So we were able to take one of our equations and solve for it that way. Because we'd separated, that was one of the equivalents that we were able to make because everything's in equilibrium. Okay, so now that we have part B, you can either jump ahead and do part C and just get that out of the way, or we'll go back to A first, and then we will then go to C. So part A asks for tension Y, right? So we'll do basically the exact same thing. Tension in the Y plus tension of spider in the Y has to equal 0. Because it's not going to move, right? So we have tension in the Y minus 0.15 cosine of 57.9 equals 0. So you just add that over. 0.15 cosine 57.9, which will equal 0.08 newtons. which is really small. Ty is not doing a whole lot. But that's how we can find the other tension. You can't find those sides of a triangle, right? We've got all these different tensions. We can't find all of those tensions if you don't have angles, right? You've got to have angles to work with in order to do that math. Now, next and last but not least, part C, it just wants to know the angle of angle C as we put it. I made it B and C for that reason. So B and C complement each other. They make an even 90 degrees. So B plus C must equal 90 degrees. It means that C is 90 minus B, which is 90 minus 57.9, which means that C is 32.1 degrees. All right. So that's how you do that. Remember, the setup is the harder part in that problem. Try and make these triangles when you're doing it. These are the, let me load it. Oh, keep moving. There you go. So those triangles are going to be key to your success. You may not want to label them B or C. I labeled them that just because that was part B and part C in the problem. If you need to label it whatever you need, go ahead. But you got to split it up into a horizontal and vertical axis, and then solve for the missing variables. Once you make those two red triangles and the gold triangle, those are basically key to solving the problem. Okay. All right, this is the last video for vectors. After this, we're moving on to two-dimensional kinematics, where we will use vectors to solve kinematic equations.